Drones are one of the most versatile all-terrain vehicles, and when equipped with the right technology, they can help us solve pressing challenges like surveillance and rescue operations. So we took it in our hands and tried to solve this problem. Here's an introduction to the flow of processes on our drone. Our drone is powered by the APM 2.8 flight controller, which has onboard IMU and magnetometer to judge its orientation, which is then fed into the extended Kalman filters and the PID control loop to maintain its orientation. Apart from this, we have an RPI on board, which reads both of the cameras used for stereo depth. We also have a phone on board, which communicates with the Raspberry Pi through sockets. We used a phone in the first place to get an idea of how GPS works and to get a proof of concept. The phone used to send GPS data to the Raspberry Pi using sockets. And then the Raspberry Pi used to send all of the data collected, for example, the images from the cameras and the GPS location from the phone through WebSockets to the ground station. The ground station then used to process those images and produce a stereo depth and a mono depth image using the MIDAS model, and then apply a complementary filter on them to remove the grainy image, to remove the grainy part of the stereo depth image, which then is used to make a 3D object. We also use YOLO on our images to detect vehicles and personnel on ground. This can be used in surveillance and to find living life during a disaster. And then we are also planning to put on a thermal camera to detect living beings faster than the YOLO model. This is all about our hardware, and later on, we will be upgrading our hardware with better cameras and LiDAR sensors and thermal cameras. We now move on to our depth perception model. We first use stereo depth. Stereo depth works on the principle of parallax, that is the same principle on which human eyes work. First, we calculate the disparity between the images and then apply some basic trigonometry explained on the bottom left of the slide. And then we calculate the distances of every single object present in the image. Over here, you can see the pillar moving around, and there's a red blob in the depth map representing the pillar. The pillar appears to be the closest object on this image. And then later on, we remove the noise from this grainy depth map by introducing a complementary filter with a mono depth AI model called MIDAS. And the complementary filter is basically a biased average, and this helps us produce a smooth depth image. In the previous footage, we saw the drone moving on the yaw axis and collecting depth map images. Now these depth map images are stitched together and then plotted on the XYZ axis to create a 3D object like this. This can help in rescue operations where the drone is traversing in caves, and then you can map out the cave and then later on send a manned operation so that it's easier for the people to rescue the victims as they now know the map of the place they are exploring. Now you can see our YOLO model in action. You can clearly see that it can easily detect people on ground. Over here we have a sample input video and the output of that video showing all the vehicles and people marked in a box. You can also see that on the top left of the frame, we have the frame count, the number of people in the frame, and the number of vehicles in that frame. Next, we move on to one of the special features of our drone, that is the loiter mode. The loiter mode basically helps the drone maintain its own position without any human interference, making it easier for the human operators to fly and learn how to fly the drone. As you can see, when I switch the flip and turn off the loiter mode, it gets quite difficult for me to control the drone. This feature can be extended to autonomous flying by just simply putting the waypoints. The drone will now fetch its new target and go to that waypoint and then fly fully autonomously. In the frame on the right, you can see how stable the drone is at its own position and not moving even a tiny bit. Now we can see the app we built for sending our GPS location from the phone to the Raspberry Pi through sockets and then to the ground station through WebSockets. The terminal over here is open on the ground station. You can clearly see that the phone is sending its latitude, longitude, and yaw heading clearly through WebSockets. We first did this to get a proof of concept. We took this data to the Raspberry Pi and then through UART we fed it into the APM to check if modes like loiter and autonomous flight do work. And then later on we invested in a proper GPS module. Over here you can see the GPS data we collected from our app, and we have also plotted it on the map for easier interpretation. This frame shows the data collected by the APM 2.8 flight controller. Over here, you can see that the orientation, the yaw heading, the GPS coordinates, arm or disarm status, everything is recorded by the APM 2.8 and then later on sent to the ground station through radio frequency telemetry. We have a modular clip attached to the bottom of our drone, which helps us with various attachments. Over here, I have designed one such attachment. During disasters, meal ready to eat, that is MRE, is distributed, and this is a cartridge to fill MREs in and then drop MREs one by one. You can see the blue plate sliding out. The blue plate will be used to keep the MRE on top of it, and then it will be slid out so that it can be dropped to the victims in need. In the future iteration, we are excited to implement real-time kinematics for centimeter level precision to allow our drones to fly in a swarm. Attached are some pictures of our drone. This whole project was done at a cheap cost of 23,000 only, making this solution cheap and feasible.